Blood is an incredibly dynamic, high-pressure fluid. To keep a human alive, it has to flow completely freely, carrying oxygen and nutrients through thousands of miles of vessels without ever solidifying. But this massive pressurized network relies on a shockingly delicate container. The barrier keeping that fluid inside your veins and arteries is an endothelial lining exactly 1 cell thick. When an injury occurs, mechanical trauma violently rips those endothelial cells apart. The structural integrity of the vessel is suddenly shattered. Instantly, pressurized blood bursts through the microscopic opening, escaping the vascular system and bleeding out into the surrounding tissue, or entirely outside the body. If this leak continues, the body's internal blood pressure will crater. The organism has only minutes to build a physical seal over the breach, or it will die. To stop the leak, the body initiates a desperate first response protocol called primary hemostasis. This diagram shows what happens next. Disc-shaped cells called platelets rush directly into the tear, snagging onto newly exposed collagen fibers to form a temporary barricade known as a platelet plug. These platelets aggregate quickly, but their physical connections are weak. They lack real structural integrity. Behind this fragile wall, the heart continues to beat. The sheer mechanical force of the blood pulsing against the plug threatens to blow right through it at any second. A stack of loosely bound cells isn't enough to hold back systemic blood pressure. To survive, the body needs massive, heavy-duty chemical reinforcement. That reinforcement arrives in phase 1, initiation. Resting just outside the bloodstream is a scout protein called tissue factor, positioned specifically to detect a breach. The moment blood spills out of the vessel, a circulating protein called factor 7 collides with that tissue factor. Their chemical clash generates a tiny, localized spark of a master enzyme called thrombin. That spark acts as an alarm bell, waking up dormant support units, factors V, 8, and 11, in phase 2, amplification. If a mutation removes a link, like factor 8, the signal hits a dead end, breaking the chain and causing hemophilia. But in a healthy system, the activated factors race to the site of the injury. The alarm has sounded, and the cellular machinery is ready to launch a massive counterattack. Phase 3 is propagation. Those newly awakened proteins assemble on the jagged surface of the activated platelets, interlocking to form the intrinsic tenase complex. This physical complex acts as an enzyme factory. It triggers an explosive biological chain reaction, converting vast reserves of stored proteins into an overwhelming burst of active thrombin. Mapped out on this medical schematic, that massive thrombin army attacks a circulating protein called fibrinogen, slicing it down into individual fibrin strands. Finally, factor 13 takes those newly cut strands and locks them together, weaving an unbreakable mesh over the temporary platelet plug. Through this 3-phase escalation, the body takes a microscopic chemical spark and magnifies it millions of times, building an impenetrable, permanent physical seal over the breach. But this chemical explosion introduces a terrifying new threat. If this self-amplifying chain reaction isn't forcefully shut down, it will spread through the entire vascular system, turning all the blood in the body into solid blockages. To prevent circulatory collapse, endogenous fail-safes arrive. Notice the anticoagulants listed in this diagram: protein C, protein S, and antithrombin 3. They go to work immediately. Protein C slices up factors V and 8, while protein S suppresses factor 9, cutting off chemical supply lines. By destroying the activated enzymes as fast as they escape the injury zone, these inhibitors fiercely suppress the clot, confining the solid mass to the exact millimeter-wide location of the tear. The survival of the organism relies on this ruthless restraint. The ability to abruptly halt the clotting cascade is just as critical as the explosion that started it. Days or weeks later, the underlying tissue cells successfully divide and repair the vascular wall. The heavy-duty barricade is no longer needed. A specialized protein called plasmin arrives. It quietly breaks apart the dense fibrin mesh, dissolving the hardened debris back into the bloodstream. The structural seal is dismantled. The wall of the vessel is whole again, and the liquid blood now flows perfectly freely through the exact spot where the violent rupture once occurred. This microscopic ecosystem responds to lethal trauma by unleashing an overwhelming, highly localized physical force to save our lives. And when the job is done, its quiet regulators dismantle the machinery, bringing the entire system safely back to equilibrium.